online. All right, welcome back. We are Game 2005. That's Game Physics in the fall 2021 semester at George Brown, and it's week 14, part one of our, good morning, part one of our recording and broadcast. And I just want to zoom in on some stuff that we've got going on this week. So again, we're sitting at the bottom of the semester, and assignment 4 is slated to be due at the end of this week. Okay, so that's something that's happening right now. And if we take a look online, just to see when this assignment is due, assignment 4 is effectively assignment 3 part 2, and that's due so far this Friday, December 10th, 2021 at midnight. And since they're sitting at Thursday, that means this thing is due tomorrow. Okay, so how are we doing with your assignment right now? How are you feeling with it before we get back onto this? So I just wanted to talk about this first. And again, I'm looking for general. Catherine says, pretty confident, just iron out a few bugs. Table, okay. A little nervous about getting everything working on time. That's Sophia. Yeah, I know it's a lot to do. So the reason why I have a reason why I'm asking this, of course, right? I'm just trying to figure out for you, for all of you, how it's working in terms of your time frame. I know there's a lot of competing assignments. What else do you have this week? Can anyone offer up that some of that information? GL. What else? Graphics, yeah. That's OpenGL. Settings for exams, okay, fine. But so when is everything due this week? Like, you know, like what's happening for this week? Game production was due yesterday. Okay, good. So that's not so much, not so much of a competitive course or something like that. A course in competition with our own. I'm asking for a reason. I'm asking because I want to make sure you guys are okay for submitting everything for tomorrow. They're due Sunday. Okay. All right, that's good. Physics labs, yeah, that's so physics lab, graphics, general elective, and final assignment. Okay. All right. So again, I think that 10 out of 12. Yeah, absolutely. Right. And that's for the labs. Yeah, so then Joss marks those, and then I count the best 10 out of 12. For the most part, it should be, you guys should be okay. So the reason why I'm asking is because typically when we get to this part in the semester, people are dying. and I mean like a pile of work and all that kind of stuff. But if you guys seem like you guys are good for tomorrow, then I'm okay with that. We can move on. All right, so not much. Remember, we talked about this special topics. Is we're going to do it in Unity today, and we're going to spend a little bit of time in Unity, but not much, just to kind of go over some things that I would do to make some things a little easier. And I'm going to be focusing on a few things for this week again. So it says assignment 4 moved to Monday. I was going to move it for you guys, but it looks like you guys are good, so we won't do it. So I'm going to move it to what I'm actually going to do is I'm going to extend you guys. That's what I'm really going to do. I was prepared to extend you guys to Sunday, December 12th at midnight. That's when I'm going to do it. So because although you guys aren't complaining, I personally feel that from other people that have given me feedback, you guys here who are attending aren't doing much, but you're saying everything's fine. We're good. We have other assignments. But I'm going to err on the side of caution and give you until Sunday, December 12th to get this thing done. So that is when it'll officially be due, as opposed to you know what's happening. I'm definitely going to talk about the final exam. So so yeah, so that is we're going to display this until the 15th to give you guys some extra time if you need it. Okay, so I'm moving this assignment only because I want to make sure that you guys have enough time to get it all done. And I know some people don't complain, and then they ask me at the last minute for extra time. They're like, Tom, I need some extra time. So being preemptive, because I've seen some emails come through that have been like, I'm really struggling with this, trying to understand stuff. There's a lot going on, and so on. Especially since you guys are still, all of us are in this remote state, and all that kind of stuff, which I understand because we're all in the same boat when it comes to this. I'm just preemptively updated it to Sunday. Okay, so and this way, people, instead of asking me for extensions and all that kind of stuff, it's just done. Okay, so that'll give everyone a chance to, to move forward and understand what you're doing. And one of the questions I just got, can I talk about the final? Yes, I can. Let's talk about that a little bit. So again, one thing I'm going to do is I'm going to release it early. So that's going to be next week, Monday. It's going to be practical. So that's one thing you're going to need to know. It's going to be individual. So it's not going to be something that you can combine with somebody else. It'll end at the end of the week. So far, it's slated for Friday. So you have from Monday to Friday to get it done, right? I'm not going to kill you with time frame. I'm not going to make it very challenging as an assignment. You're going to get, it should take you about 2 to 3 hours max to complete it. So something that you could have done in class is how I would slate this thing. And again, there's no lecture next week on Thursday, but I will have office hours during our lecture time, and to answer any kind of questions you might have regarding the exam or anything like that. That is what's happening for next week. Okay. Rich is asking, what would you focus on? I would focus on all the stuff that you've done so far in the second half. It's not going to be based on the first half at all. So anything that you did in the first half, it's not relevant to what we're doing in the final. So yes, assignments and labs. So the things that you've been working on in your assignments and the labs kind of knit nicely with them. Joss has really worked hard to create labs to help you with your assignments. So this week effectively would be your last teaching lab. Next week is more, he's going to be around as well during a regular time frame for assignment help or exam help, but you have the entire week to get it done. Okay, there is no timing for this thing. It's Neil says, so once we start, we have to hand it in within 2 or 3 hours. No, you have until, and you can start and end from Monday to Friday. Okay, you don't have to start the assignment or end the assignment at a particular time. You just have to submit it. Just like it would act like a regular assignment, not a test. Okay, but it's a week-long assignment that you take home. It's a take-home test, and then what you're going to do is you're going to produce something that is derivative, something that we've already done from our I've already asked you to do in class. As an example, we've talked about it in class, or you've done it within lab. It's going to be based on something like that. Okay, and it'll be based. You'll probably get a starter or whatever to work with, and you'll be asked to implement some stuff or build on something that you should already have. Okay, so that's how it's going to be. It's not going to be that difficult. At least I'm going to push to make it less difficult. I know that that Joss is, he wants you guys to get the concepts and to understand how things work. And that's what we're really focusing on. Things to study. People ask things to study. Let's talk about that a little bit before we move on. So we talked a lot this semester, this second half, about collision detection and response. So you can definitely expect something around collision detection and response. We have both 2D and 3D collision that we've talked about, but we've worked on 3D in Unity. So you can expect that you're going to get something in Unity that you're going to have to do, and it'll be something different than what you've done already. Okay, so applying the same concepts and using the same code that you'll have from, Miguel says, I have not solved the collision response. Yeah, so you're going to have to solve it because that's something that you're going to have to work on. That's part of your assignment 3 part 2, right? Which is something that you're going to have to figure out. And if you figure it out, then you're obviously going to be able to use some of the same stuff from assignment 3 part 2 and assignment 3. I think what we're going to do is we're going to allow you to use any of your code that you've kind of developed. Um, and that means that if you're working with a group of 2 to 3, a group of 2 to 3 people, that you can all share that code base, I think is something that we'd probably allow, right? Because I don't think it's fair if only one of the people get that code. And what I mean by that is anything that's been shared with you in lab is going to be fair game. Anything that I've shared with you, obviously in class, and it hasn't been a lot. I mean, I'm just getting you to use Unity and so on. But we're going to give you a starter, and that starter is something that you're going to have to build on. Okay. Will I give you a clue on AABB and sphere collision response? Did Joss not cover that stuff at all? He didn't. Okay. AABB. Okay, we can cover some of that. I mean, remember that so what are the steps? Let's go over this. Let's talk about collision response. What are the steps as an overview to collision response? What do we do? What's the first step? First step to collision response, guys. What do we do? Okay, find the displacement. Okay, get the collision detection. Yep. I think the first thing is, do you overlap? Right, that's the first thing. So if I was going to write it down, let's write it down together since we're talking about this stuff. So let's think if we can, kind of summary of collision response. All right, let's do it together. All right, so if we're going to think about this, the first thing is step 1 would be first collision detection. All right, so that's step 1. So let's just do this in steps here, and that's so that we can specify. And that means things like overlap detection. That's what we're doing first, right? So that would be the first thing that you would do with AABB to AABB, right? AABB to sphere, right? And at least AABB to sphere to sphere, sphere to sphere. Those things, at least at the very minimum, you need to know how to do those overlaps. Okay, so those cases: AABB, 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 sphere, sphere, sphere. And I think it's also, if I'm not wrong, we may have to do AABB to plane, right? In terms of like collision detection, because you need to do that, and also plane to sphere, or sphere to plane. Sphere to plane, because you need to know how to set a sphere onto a plane, those kind of things. You should know that first. Okay, so that's the first step. So okay, so next step. Let's do some, the next part, which is what you guys have mentioned already, some of you, which is overlap. So how much displacement, how much overlap, right? So how much did you overlap? You remember that what we talked about was this idea of, as an overview, right? When we have two objects, whether we have this one, let's just use another kind of object like this, right? I'm just using these right here in PowerPoint, right? So let's do this thing. So if I have this object here, right, which is some kind of cube, or in this case it's a square, rectangle. And if I have an overlap, how much do I overlap? What is the overlap? What is the overlap distance, right? And the other thing you have to think about is what you would do is you take, kind of the amount that's been penetrated, how much the penetration distance. So again, you find the penetration distance. Well, I think Joss covered that, I'm pretty sure. He probably talked about penetration distance, and then divided by 2, right? So once you take that penetration distance divided by 2, how much you need to reposition, right? So that's the next part. So overlapping stuff, right? Yep. So the final penetration distance, and then the normal. So this is the collision normal, right? This collision normal is the direction, right, of the collision. And a lot of times it helps when, even if we have 2 moving objects, let's suppose this cube and a sphere are both moving, you select one of the objects to be not moving. All right, so you say, okay, well, if this is something that you're going to figure out, right? As an example, let's suppose that the sphere isn't moving, or the cube isn't moving, but the sphere is. We get something called the relative velocity, right? So we need to find relative velocity. That's what we need to find. And the relative velocity is, if this one was moving at a speed of, let's suppose, I'm just going to put some arrows here. So let's make an arrow that goes this way. Oops. Let's put that arrow like so. Let's make an arrow this way. And let's suppose that arrow, we're moving at a certain speed. And let's say we're just moving it exactly in a perpendicular type of collision like this. So we have two arrows, they're moving in different things. You kind of, what's the relative velocity if the arrows are moving directly at each other, right? So what does that do? If I take an arrow, let's suppose what's an easy way to get this done? And so if I look at a text box, and let's say, for example, I'm moving at 5 meters per second. We're just to use math here for a second, right? So if this one is moving at 5 meters per second in this direction, and if this one is moving at 7 meters per second in the other direction, what's the relative velocity? And if they're going to collide this way. And let's say this is the positive direction and this is the negative direction. So, okay, there's a couple ways to think about this, right? You can add them up, right? Because you're moving that fast. You're moving faster. If one wasn't moving, right? Let's say, for example, this one here was at 0, right? And this one was moving at 7 meters per second, right? Then the relative velocity would be 7 meters per second because it's moving this way. But if you're moving at 5 the other direction, now you're moving together faster than you would normally move, right? Getting the actual velocities of the objects is important too, because you got to figure how much one object would penetrate versus the other. Okay, so that's something to understand too. So if they were the exact equal, if they're both moving at 7 meters per second, this is one case, right? If both they're moving at 7 meters per second, and now they're moving at a relative velocity of 14 meters per second. If you actually use one object that was this scenario is similar to if we said that, let's suppose that this object here, right, was moving at 14 meters per second. Yeah, it's kind of like that, right? Because it's like these two objects are moving together, and if this object was stationary and this object is moving at 14 meters per second, the penetration distance might be the same, right? So, I mean, it's kind of the same, or the other way around as well, right? So a lot of times, to simplify, right, we do something that looks like this. We do this, right? We say, okay, so how much is this going to penetrate, and when did it happen? So this is not just find the penetration distance, the collision normal, and the relative velocity, but also when did it happen? So when did the collision occur? And where? So when and where? So when I say when, I mean, like, did it happen, last frame, as an example? When we penetrate, I'm saying when there's an overlap, when did it happen? And then backtrack, go to the previous frame, that kind of stuff, right? So, and where would be like, where did the collision occur? Like across which edge or face, or what's the closest point, if you will, right? And this is the closest point. So you can find all this closest point is also important. So let's break this down into a couple of different lines here. So when we can figure that out, but where did the collision occur might be most important. So where did the collision happen, right? The closest point, right? So what's the closest point of the collision, relative to the object, right? And finding the closest point is something that is very important for us. We talked about this because once we know what that is, that's important. The collision normal usually has an angle. It's usually not like this, okay? It's usually like there's some kind of angle. So this might be something like this, and the arrow might be kind of this way, right? So these two objects are moving together, and this is where relative velocity you have to kind of figure out, well, where, if I was going to take these two objects, would the resultant vectors go, right? Because that's important to know as well, right? So example, if this was both moving at and this is kind of drawn wrong now. Let's suppose it's something like this, right? And if I was moving this one at 7 meters per second, right? Then, and let's just take this away, right? So then now, how does this look in terms of, the where is that going to collide? How do we figure this out? Because you have two shapes, right? And you have one shape that's traveling in one direction and another shape that's traveling in another direction, right? And then you're going to have a resultant vector, right? There's going to be a resultant thing. And we're not even talking about mass and all that kind of stuff yet. We're just talking about, finding whatever this collision normal is going to be, right? So that's the first thing. So yeah, so this is closest point, and we can also call this the contact point. So if we think about these things, these are the things we want to know, right? So this is relative velocity, this idea of where they're going, and the finding the collision normal is kind of an important. And all this is part of something we call the collision manifold. This whole thing is part of the collision manifold, figuring that out for each of the objects, right? Okay, so once we find how much overlap, then what we want to do is we want to reposition, right? So that's the next part. So there's some stuff we've skipped here, obviously, but we want to reposition. And we want to reposition both objects, and this should be across or aligned with the collision normal, right? So that's what we want to do. So whatever that collision normal is, we want to kind of zap back in the opposite direction just to reposition. Okay, so that's the first thing we want to do before we move on. Does this make sense? So collision detection, how much should we overlap? Reposition back, and we want to kind of reposition half the distance, half the penetration distance. Move back half the penetration distance. This is something that we can do, right? It might not be fully accurate, but it's probably good enough, right, for what we can do. I mean, it's yes. So what you're saying is, is it like the box normal? Think about it like a collision direction. Instead of let's not use the word normal. Let's use the collision direction, right? So if I have, the area or kind of the angle of incidence. What's the angle of incidence? When do both things collide, and what's the angle for each thing? Kind of idea, right? The easiest one obviously would be to have a dead-on or head-on collision, right? They would just smack back in the opposite direction, because now the angle of incidence, collision normal, the direction of collision, or we can also call this the angle of incidence, right? So whatever the angle of incidence are, you want to go back across that angle, back the other way, right? So you want to reposition, move back half of the penetration distance, and now you want to preserve, or what we like to say, conserve momentum, right? So you want to kind of calculate whatever the momentum is in impulse, right? And do that thing. So again, calculate impulse and momentum. And momentum has to do with mass and velocity, right? That's what it's all about. So we want to know what the masses and velocities are. There's some formulas that we can do, right? And we also want to take into account friction and restitution into account, right? Because we want to know those two things as well. Let me just get rid of all this now, as you get the point of this. Right, so we want to take restitution. So friction, is how much energy loss, and we also need to know the friction direction, right? The direction of the friction, as well as restitution, how much bounce. And the more restitution, the more of an elastic collision you have, the higher the restitution number. Usually the restitution number is normalized between 0 and 1, and we have to decide if it's closer to 1, that means it's 100%, kind of elastic. And even if we have a higher friction, the friction is just going to slow it down, but it's not going to stop the bounce. The bounce is like going to actually increase. A lot of times what we want to do is there's friction and restitution to account for each object. And like we talked about last week, we want to calculate the average. Typically, we want to calculate, or we'll say compute the average friction and restitution. Sometimes what people do is they don't take the average, take the maximum or the minimum. So somehow you want to combine it somehow. So you want to combine, let's call it this way, combine friction restitution in some way. So whether it's average, whether it's min, max, and so on, right? You got to figure this out. And that's, you'll figure out how much momentum that you're going to have. You're going to calculate the impulse. The impulse is going to tell you how much energy is going to go in a direction. And then you're going to, you can understand where, how we're going to reflect off the surface of where you're looking. So again, reflect your object in the correct kind of angle, right? So basically, as you hit, you're going to reflect back out in the correct angle, and with the correct velocity. That's what you want to do, right? And the velocity is going to be correct based on the impulse and momentum, mass, and all that kind of stuff that you're calculating. Is going to take it's going to be effect. The friction and restitution also play a part, and then you're going to reflect it back, and that's really the 4 steps for the most part at a very high level, right? Yeah, so it could be perpendicular, perpendicular to the surface, that's for sure. It's going to bounce, again, there's 2 things, right? Whenever we looked at some cases for bouncing, we said that there is if your bond's bouncing off of a horizontal surface, directly horizontal, with respect to the y-axis, vertical, with respect to the y-axis, a vertical wall, then what you're going to do is you're going to keep going in the same direction. As an example, that you're moving from a vertical perspective on the y-axis, but you're going to bounce back on the x-axis and reflect on the z-axis. So that's important as well, right? So if you're going towards the z-axis, here's an example, right? So if I'm moving in towards the z-axis generally, right, and I have some energy going on the x-axis, but I'm hitting a vertical surface, right? So I'm kind of moving, kind of positive on the z-axis. That's into the screen, right? And then I'm bouncing, back along I'm bouncing on a vertical surface, right? Then I'm going to reflect wherever I was going on the z-axis. I'm going to be back the other way. That's one. And what about the x-axis? The x-axis is also going to have a reflection. So if I'm moving across the x-axis in a certain direction, then again, I'm going to keep going, but I'm going to reverse the x-axis as well. So the x-axis and the z-axis are going to be reversed, but the y-axis is going to stay the same. Typically, that's what happens. All right, more or less. Okay, and the other way around is true as well, right? If I hit an object on a horizontal surface, like a table or something like that, then what's going to happen when you hit the horizontal surface and bounce, you're going to keep the energy, as an example, across that horizontal surface, right? But you're going to reflect, you're going to reverse it across the other direction on the y. Yes, I think so. Yeah. So that's the thing. So when we do a bounce like that, we got to think about, some simple cases that we want to deal with. But this is more or less what we do. First, the first part of doing collision detection is, or collision response is good detection. Can we detect right? So you need some kind of collision manager in play doing this kind of stuff. Then how much did we overlap? Detect the overlap. Sometimes we have to do contact points. By the way, the other thing that we want to think about is some optimizations, right? So we haven't really talked too much about optimization. Let's do, how about collision optimization, right? So things like we can talk about broad phase, narrow phase, which harkens to something like a division scheme. Okay, so we can do something like this as well. So division scheme means that you might want to think about things like grid, or some kind of, you know, sparse voxel, uh, kind of collision detection, or one of those kind of things, right? So we can do in 2D. We can do we can break things down into quadrants, right? And in 3D, we do it. We have octants. Octets, right? So whether it's quadrants or octants, right? So we kind of break it down into different, thing. And remember, we talked about this. If we make a grid or some kind of quadrants, octants, we do slices, world slices, right? We have something like that where we do those kind of things. And the reason for this is because um, we don't want to collide with everything. We want to avoid this kind of thing. The other thing that we want to try and keep in mind is, select an appropriate data structure, right? So sometimes it's using a tree type data structure, or we might use a queue, right? As an example, we load everything onto the queue, and then what we do is those are all the different collision detections that we have to kind of work through, and a collision queue would be would use messaging, right? So we could use even the observer pattern for this, right? So let's talk about the observer pattern for a little bit, and talk about how this works, right? So again, the observer pattern, we'll say the observer pattern for collision detection, and the way this can be working as well, instead of just the way it's working right now, is you think about things in a little different way than what we're thinking about today. And the way it works is you have, and let's see if I can look up a little diagram for you guys so I can explain it faster than what I'm doing here. So let's look up the observer pattern. And if I look at the observer pattern, I just want to see one image yeah, perfect. So this is the idea. This is not bad. I'm trying to look at something that is subject. Yeah, something that looks like this. But let's grab this image here, and we'll use that one. Okay, so the observer pattern, and I'll kind of cite this image later. But really, what we're thinking about when it comes to the observer pattern itself is we have something called the observer, and what we have is a subject. All right, so something that is observable, right? So what we want to do is the subject. Notice that there is a couple of methods here. These are, by the way, abstract classes. And we have a notify method that's part of the subject. The subject itself has a bunch of methods that are in it that you can add an observer or remove an observer. So the observer kind of watches an observable. Okay, so let's think about this as an example in another way, and let's try it in like this. So let's suppose I have an observer, right? Okay, so let's do this like so. So here's the observer. And you can have any observer class, right? The observer wants to subscribe. A lot of times the observer is also called a subscriber, right? So, and by the way, this works with with other things as well. So subscriber. right? So observer or subscriber. Sometimes they're also separated depending on the way it's worked. So the subscriber subscribes to some kind of event that's going to occur, right? So for example, subscribes to an event, right? And let's just call this the event subscriber, as opposed to just a subscriber. So what kind of event would this be? A collision event, right? So that's what they subscribe to. And when they subscribe to a publisher. Okay, this is the publisher subscriber pattern as an example, where the publisher would be the subject, if you will, in other cases, right? So we'll call this the subject. And we'll also call this the publisher. So the publisher has a way of notifying all the subscribers or the observers, as an example. So that's what they do, and they have a notification list. So let's make some patterns here again. We have a list of subscribers, right? Subscribers, right? Or a subscriber list. Let's call it, actually, let's make it like that, subscriber list, right? And what we want to do is when an event occurs, right, that the subscriber or the subject is taken care of, right, or watching, if you will, it's going to notify its subscriber list, right? So there's notify subscribers when event occurs. Okay. That's what the job is of the subject, right? It notifies subscribers when the event occurs, okay? And so why do we want this pattern? Because the subject is looking at a bunch of events that occur in some kind of queue, typically. So this is like a, yes, it's exactly like how that's like, guys. So we can see this as an event queue, right? And this event queue, right? And you can have any kind of event, a mouse click event or a collision event as well. So what happens is the subject, right, or the publisher watches this observable area, and we're going to call these this is the observable queue, if you will. So this is the observable event queue, something that can be observed. Okay, and it watches in this queue for an event to be raised. We call it an event is raised or added to the event queue, right, as an example. And once the publisher sees that this has happened, it notifies its subscriber list that this event happened, right? It notifies the subscriber list, all right? That's what happens. So it watches, the subject watches or observes the the event queue. It's listening or tied into the event queue. Sometimes the subject is also called or also can have a middleman, which is the listener, all right? But sometimes the subject and the listener are one. It really depends on how you code it. So let's put in listener here as well. So there's the listener or the watcher or the observer, call it whatever you like, right? Sometimes the listener and the watcher and the subject are watching for an event to occur, and then the observer subscribes to the event. They're the subscriber, and the subject notifies them that it happened, and then the observer decides to do something, and they might notify the handler, right? So there might be another step where there's a handler that's also subscribed. So the observer is also, or the subscriber is also a publisher, right? And it has a handler, or let's just connect to a handler somehow, right? So maybe it's associated with a handler. And this handler typically is, this handler is something that's going to handle the event, okay? So we can do it haphazardly because we're talking about collision optimization. We can do something like, okay, I want to check every object with every other object. Yay! And what's that going to do? Well, whenever we do a check, we're doing it here. We're checking in the publisher. The publisher is watching for collisions to occur, and then it's going to notify its subscribers when it happens. Okay, we can do that. But it's nice to have an event queue, something that happens. I have a collision, AAB type collision detection. Let's put those in there. So we can have that, right? We can have an AABB. Oops. Let's undo that change. I would rather have it as separate items so I can show you. So something like AABB to AABB type collision detection, right? ABBA. I'm going to spell ABBA pretty soon, right? So that's one type. Or we might have another one that is a AABB sphere, like we say. Or there might be another type of collision detection to happen as well. So this is how we can do collision optimization. We can kind of put them inside this event queue, and then with the event queue, we have a subject that's watching, right, as an example, and it kind of notifies all of the all of the observers that this is the truth. This whatever observer has subscribed, right, to this event to happen. So who could be the observers and who are the subject, right? You can make the subject or the publisher some kind of manager as well. Right, so you can say that this is like your collision manager, right? Like we've done in SDL Engine. We kind of have a collision manager, and the collision manager basically detects all the events and also handles them. But what we can do is we can say that the collision manager notifies the observers or the subscribers to this event could be the objects themselves. So each observable is also a subscriber, right? Each of the observables, the things that happen in the events, each of the observed events, AABB type thing, or AABB sphere, or sphere, or whatever, those events, the objects themselves are subscribed to their own events. So to know that this happened. But the collision manager manages it all. It kind of says, yep, I'm checking. But the only time I'm going to check is if somehow you're close enough. I'm not even going to raise an event, an AABB type collision detection event. I'm not even going to do this or even look there unless you're close enough. It's not even going to be part of the queue, right? Until that's happening, right? So there's a middle check here that's happening, which is the check, right? So the observable queue is when a collision occurs. That's when it does happen at the beginning, right? But yeah, let's just do this. But this stuff is actually way over here, and there's something in between to determine when to check, right? So it's almost like an engine or the division scheme to know when to check. So, this is kind of a filter, if you will, right? And this filter determines when I should check. Okay, and that's what we're saying. Instead of directly checking every single time in the event queue, right? Whether you do it that it's more organized or whether you do it so that it's less organized, really, at the end of the day, you're doing something like this. You're saying, check the event queue, right? So check to see if I've got a detection there. Add something into the event queue when this filter decides that I should be checking. Okay. Otherwise, don't do it, right? Otherwise, because I'm checking too often. I don't want to check this thing too often because it's computationally, expensive to check, right? Especially when I have thousands of objects out there. And when it comes down to the topic of today, which is particle systems and collisions with particle systems, then if we have thousands of objects in the scene, like little objects, then it becomes, it kind of bogs down, how that all works. Okay. So those are the two things you should consider. So the first part is, how do we do collision response? We think about collision detection, and we can optimize this, right? And then we determine how much of an overlap, repositioning, kind of countering the overlap, because and the overlap, by the way, the reason why it occurs is because of our time division schemes. So for example, the more frames, right, less overlap, right? In other words, the higher the frame rate, the less of this we need to do, right? But the higher the frame rate, that means your machine has to be pretty performant to work like that. That's why, it's better to calculate this kind of stuff on lower frame rates, like 60 frames per second, compared to 100 220 or 240 frames per second, which is, machines are pushing that these days, right? They're trying to push out as many frames as possible. If you're frame limited in a game, right, then that gives you the same performance for the most part across all hardware. But if you're not frame limited and you're going to run as fast as you can, right, and I'm talking about not the game to run as fast as you can, but the update to run as fast as it can, right, as fast as it can. Again, it's getting input as fast as possible. It's computing many more times per second. If your computer has the ability to do that, or either that through by single or multiple processors or processor cores, right, then obviously we're going to have less overlap, right? Because the reason why overlap occurs at all is because we check in one time, and then we wait to check again at the second point of time. And meanwhile, the object has moved because we're updating an object, and both objects have moved through each other, right? But if you check more often, right, or if you're moving slower, then there's less overlap, or less chance that you'll hit the tunneling effect that can happen if you're really moving fast, right? So again, the idea here is the difference between dynamic collision detection and discrete collision detection. Normally, we suffer, overlap happens because of discrete collision detection, because we're colliding at certain fixed intervals, right? Or checking collisions at fixed intervals, right? So this is, the overlap can be countered by that. More frames, less overlap, right? Repositioning wouldn't have to happen if we have less of this. There's going to be some, no matter what you do. And the main idea is, what is the collision normal? What is the angle of attack, right? And how much do I have to reposition back to where we actually had a collision? We're going to go half the distance is what we're looking at from one side to the other. And then finally, conserving momentum, figuring out a friction and restitution system, which is one part of assignment 3, part 2. And that's something that you guys should be figuring out. How much friction is there? If I apply friction to a surface, when I'm actually colliding with the surface, right? So I'm not allowing you to penetrate. I'm preventing penetration of a surface because I've got my repositioning thing happening all the time. Every frame I'm repositioning. I'm not allowing you to do that. What's happening. The other thing is that motion is something else we can and the whole physics system itself. Okay, so we talked about collision optimization, but what about physics optimizations? So let's think about this: physics engine optimizations, right? How about some other things, some ideas here? Putting objects to sleep. Okay, so what does that entail? Putting objects to sleep is like, okay, so the object isn't moving anymore, right? As an example. I know that, did Josh talk about this at all, guys? Putting objects to sleep in your physics engine? Yes, no, maybe? All right, so think about this, right? You have an object and it has zero velocity, right? So the velocity is completely zero. There's nothing, right? I don't have velocity at all. If I'm not moving, it's asleep, right? And if it's asleep, stop simulating. So stop simulating on objects with zero velocity. Put them to sleep. Mark them as sleeping, right? So if they've settled into place and there's no velocity, right? As an example, there's no bounce and it's stopped moving and there's no more energy, right? And we should also, not just velocity, but momentum, with zero velocity and momentum. So the momentum is zero, zeroed out. There's nothing there. There's no kinetic energy anymore, right? So zero velocity, and we'll call it movement energy. How about that? Movement energy. Because that's what it is, right? So there's no more movement energy inside this thing. You've got no potential energy anymore. It's sitting on top of a surface and it's not moving, right? Stop simulating, right? If you stop simulating, that means I'm not applying gravity and all those kind of things on this thing at all. Then that is also going to save me computations, right? If I'm putting objects to sleep, right? So that's something that is the number one thing that people do, and you'll notice it in things like Box 2D, right? So again, how it looks If you put objects to sleep, put objects to sleep. Let's look at box 2D physics, right? And let's see if there is something like that where there is. We'll look at a animated GIF, right? To see what that looks like. Yeah, something looks like this. And let's visit this thing, and hopefully, yes, continue. I think it's okay. Let's see what happens. Worst case scenario. Yeah, so you have a lot of these things. I wonder if there's an interactive demo. So these objects here, these are all objects as an example. And what happens is you can put these objects to sleep. By the way, guys, there's tons and tons of tutorials out there that you could find. Here's just one that I've noticed in terms of particles for detecting things, right? And as soon as this object goes to sleep, it changes color. They usually change the color of the object. So notice that objects that are moving, they're this color, and the objects that are asleep are this color. That means these things aren't being simulated right now until they get hit. As soon as you have a collision, right? So turn objects on, right? So wake objects, right? That's something we have to say. Wake objects if a collision occurs is what you want to do. So you only wake objects when you've detected a collision, all right? Otherwise, if the object is sitting there, leave it. Don't even look at it, as an example, right? And so what you can do is you can set up a list of objects that are awake, right? That's what you want to do. You want to get this list of objects that are awake. And this list of objects that are awake are the only ones you're going to update, right? Only update this list, right? So you don't care about the other ones because they're sleeping, right? And the ones so this is a way of improving your stuff. So I'm not simulating physics. Like that means gravity. I'm not adding velocity. I'm not doing any of those checks anymore. I'm not even checking that object, right? Now, as an object approaches the object, let's say if wake objects, if a collision occurs, and then sometimes what we want to do is do something like predictive collision detection. This is important to do as well. And doing predictive collision detection is like, I'm going to get hit. It's coming. Wake him up, right? Kind of thing, because I'm going to get hit now, right? So, so this is the way you can optimize. Some things that we talked about are optimizations, right? Questions around these things. And this is just review. These are things we've talked about a little bit here and there, and I'm just like you and I are just putting this together here in this PowerPoint, so we can look at things that that can potentially help you in your assignment 3 part 2, right? So we've taken you most of the way there, okay? And now it's for you to figure out. And what I recommend is do small tests. Don't try and do tests with like 30 objects in the scene. Start off with 2 objects in the scene, a sphere and a cube, and see what happens. Can you do a proper collision detection and proper response with 1 sphere, 1 cube? Can you do it? Yes or no? And once you have that, try with 2 cubes. Can you do 2 cubes? Can you do with 2 spheres? And then once you can do 2 spheres, 2 cubes, cube, all those kind of things, now add more objects. Don't stress test the crap out of things right away. Start off with a small amount, kind of work out different cases, right? And make sure that your code is resilient enough and robust enough so that it can handle more cases for those objects themselves. Hopefully that helped, that little talk. Because I think some of the challenges are when it comes to young programmers is figuring out where to start and what to do. Yeah, I know, right? Because when you start thinking about stress testing, like, collision detection at all, right? And having all those things move around and just doing separation. The first part was all about separation, right? It's all about, moving things back to where they're supposed to go, right? So let's do a little bit of extra stuff with Unity. So we have this little box, and what we did last time with our starter is we fired a bullet and different kinds of things at the starter. So things like building up a collection of objects. I'm just going to kind of exit out of that, so it's making me dizzy. And I want to do some highlighting when it comes to two things colliding, right? So I want to kind of see for myself, and I want to get some feedback. One of the biggest problems we have is debugging, right? So I'm going to show you some debugging techniques today on how to debug stuff that is colliding, right? So I'm going to veer away from some of the stuff that Joss has done. It's not going to collide with anything that he's done. Sorry for the metaphor. Let's add so here we have the box, but I want to add a cube, a crate of some kind that's in the scene. Okay, so again, I want to add a model. Again, I'm moving on with the assignment 3 part 2 starter. That's where I'm at. So you can use that thing from last week if you want, or any other project that you want to start off, right? It's totally up to you. And I want to add a cube, but I also want to get a crate texture, right, for this. All right, so let's do that. Isn't there only a few objects in the scene? Do you have to worry about efficiency? Yes, but when you keep adding more bullets, you will have to worry about efficiency, Neil. Right? The bullets aren't going to disappear. They're going to land and they're going to kind of accumulate, right, inside the box, right? So theoretically, yeah, there could be some difficulties. By the way, what we said in the assignment 3 part 2 is that you're sitting on a table, right? So if we bring up the document one more time for this thing, so let's bring up the document. And I want to just go over this with you one more time, right? So just to make sure we go through all the fine details, right? Because that's important. So what we drew here is this, a box, right? And it's got these cubes or rectangular prisms that are above it, okay? That's what we drew. So this is something. What happens when objects fall off? You know, I mean, again, you can make a death plane. So when objects fall off, they disappear if you really want to. If you made a pit ball, like look at it, says create a stack of small blocks on top of a larger box, right? So that's what Joss was recommending to you guys. And the reason why we want to do it this way is because if we made it inside of a pit like this, the problem with this scenario for our box is that you're going to do plane and AABB type collision detection, right? So if you did this as an example, that's okay. You can continue with this, but you have to calculate what the box and plane AABB collision detection is happening when that's happening alone. So what we're going to do instead is, what if we were to make a bigger box that takes the place of this thing? So let's just hide this one. In fact, notice that our model, we have a prefab that's the box. So if I was to delete this thing, it's not like we're going to lose anything. Okay. Let's add a big box, if you will, and that'll just be a big crate or something like that. So again, I'm going to add in a cube. And let's make this pretty big. So really, really big. So let's do that. So we'll say that it's a size of, like, I don't know, 10 by 10 by 10. So that's a pretty big box, right? And let's reset it. So, sorry, undo. Let's reset its X and Y and Z positions so that it's in the middle of the screen, right? And again, we want to add a material to make this look like something, right? So let's get a crate texture. So crate texture. So let's see if we can get that. And a crate texture is a different kind of texture, right? So let's see if we can get this. So it says crate 3D textures. Let's see if we can get one. We want something like this, a wood crate, right? It may not look like it has a wood crate, but we'll put a crate texture on it. This is what we want, right? So how do we get something like that? If I want to download it, is there somewhere we can download? Download all the maps, sure. Or maybe we'll just to simplify, instead of making it a crate, because we have to, kind of map everything on different surfaces, and the normal map has to be correct. I could do it in Blender, but let's just make it simple and just add a color for now. Sorry, I'm going to make it this brown color. So that's your crate. Okay, how about that? And what I want to do is I want to add some, and we'll call this the table, right? And what I want to do with the table is I want to have several blocks kind of are on it. So let's add a block, right? So add another 3D object, which is cube, and we'll bring it up. There it is, right? And we'll kind of set up the blocks the way they are, and I'll make them so that they are similar to what we see in the assignment where we have these things like that. So just to do that, again, I'll use this selector over here, right? So this one here allows me to kind of scale it from one side only, which is kind of cool. So I'll make it something like that, right? And let's put some material on there. I have a blue material. We'll apply the blue material on the block, right? And then we'll have our blue block. Blue block. Okay, there's a blue block. And I don't know, what else did we have? What else do you have? He has red blocks and a gray block and a white block. Okay, so we'll just Control D, and then we'll move it across, right, kind of thing. So right next to each other. And what I want to do is we'll make this a red block. Okay, so red block, blue block. There we go. And let's get that red material on there. Hey, awesome, right? Save. So what I want to do now is I want to detect collisions, but I want to do it in the editor, right? So I want to see how my editor is working in terms of my, I want to kind of highlight some stuff in terms of my extents and those kind of things, right? So how do I do that? Which is the thing that I want to do. So I want to kind of add kind of like a, we'll call it a cube behavior on this thing, right? So again, I'll add in a brand new script and we'll call this the cube behavior, right? And I'll add the cube behavior on both the red block and the blue block, right? When it feels like it. Cube behavior, cool. And so notice that when I select these objects right now in real time, right? That's okay. But what I want to do is when I'm actually colliding, as an example, I want to find a couple of things. One, I want to find the extents of or the bounds of each of the objects. Okay, that's what I want to be able to find, the bounds. And so that's one thing I want to be able to find. Let's do that with cube behavior. So we'll do a little bit of scripting and we'll think about what I mean by this. So I want a few properties to be, and this is for troubleshooting, right? So again, I want to say public vector3, and let's think about, I want to find the size of my object. So that's, we'll talk about that in a second. Another public vector3, I want the max of the object, right? A lot of times we want that. And public vector3, I want the min, max min. I want a public Boolean, right, which is something like is colliding. Okay, so I want to detect if the thing is colliding or not, right? One day when Visual Studio decides to respond. There we go. Okay, I want that. And I want to also have a public list of contacts for each of my of other cubes that I collide with. So some kind of public list, you know, and I'm just writing this on the fly here, guys, of cube behaviors. All right, public list of cube behaviors, which I'm going to call contacts. Hey, there we go. As well, I want a couple of private things that I want to take care of. One of them is a mesh filter, right, which we're going to call mesh filter. And I also want something private called bounds. And I want you to think what bounds are, right? So private bounds, remember we kind of want that as bounds. Okay, so bounds, when I think of what bounds are, it's Unity Engine bounds. It's not my own bounds. Okay, so I'm not making my own boundary for this. I'm just using Unity Engine bounds. Okay. So that's what those are. And if you want to look up what that is, it represents an axis of the aligned bounding box. Look at that. See? The axis of a line bounding box. I'm not using, this has nothing to do with physics, by the way. This is just, the axis line bounding box and the mesh filter. The mesh filter, actually, if you look at the objects I put into place, these two blocks, they actually have a collider. We want to remove that collider because we want to do our own collision detection, right? And the same thing goes with the table. The table also has a box collider, so let's remember to remove that because we want to do it our own, right? But notice that I have a mesh renderer, right, for the box itself, right? And the mesh renderer, if I was to open it up, has a materials, right? It has lighting, right? It has probes, right? And all this other stuff, right? And the same thing goes with our cube. So this one also has a mesh filter. A mesh filter is the cube shape, right? So this is our blue block cube, right? But the table is a cube, right? But the blue block, this blue block thing is not, right? It's a cube, but it's actually a rectangular prism, right? So here's something. Let's start. Also, I'll do it on the table itself too. So let's do the cube behavior on the table for a second, right? Again, this is just for troubleshooting. So yeah. So what I want to do is in the start method, I want to start thinking about some stuff. I want to say that the mesh filter, right, that thing that I'm trying to calculate, is equal to get component, and I want to get the mesh filter, right, of the object itself. Remember, the mesh filter is the mesh that is being used to create my object. So a cube mesh, as an example. Okay, that's what it is. I also want to calculate the bounds. My bounds are going to equal to the mesh filter, right? And I want to take the mesh, the actual mesh itself, and I want to kind of figure out the bounds of the mesh. Okay, so that's what the bounds are. Remember, it's going to be stored inside of this bounds, private thing here. And then what I want to do is I want to say that size then is equal to bounds.size. And size is going to give me a vector3 object that's going to include all those things. Okay. Pretty simple. So what I want to do is I want to use all my, physics-related calculations are going to go here. Physics calculations here, right? And I want to be able to draw some of this stuff out. So we leave min and max there for a second. We'll see, and maybe we'll just reposition them so that we can actually see them in proper order. Min and max. I'll space it out so we can see it here. It's going to appear all together on the inspector, but let's take a look and see what that looks like. Right? So there's my table. We have a bunch of contacts. If we have any contacts, we want to keep track of all the contacts. And we want to keep track of the size of the table and all that kind of stuff, right? And one thing you can do to do some troubleshooting is we can add a color. For this time, I thought we were supposed to just add a color. Yeah, that's fine. Yeah, and for what we can do is, what if I want to execute in edit mode? What if I did this? Execute in edit mode, right? And I want to calculate these things in real time all the time, right? So what happens is you see that the size of the table is 111, right? And if I look at my blue block, the size of each of these things, right? It's not really reflected, right? The size and the min max, we don't have min max yet, but the size is not 1, 2.15, and 1, right? That would normally be the size, right? That's where we start off with. But what I'm looking at is what is the size of these things and what are the bounds? I want to see the bounds. By the way, if you want to make bounds public, if you want to do that, and if you thought that was something you can do, if you try and serialize any of these things, you try and serialize, and if you want to see bounds, that's what they look like. Take a look at the bounds, right? So if I look at an object like table, right, then you can see the bounds are the extents, half of the y, 0.5, 0.5. That's the bounds, okay? So whatever the object is in terms of scale, half of the extents are the bounds, if you think about that, right? That's what it really is. So 0.5, 0.5, 0.5, right? Okay, okay, I like it, I like it. Well, let's do some, the min and max. Okay, let's calculate the min and max now. And I want to do it on update, not in fixed update. You can have multiple updates. You can have a fixed update and you can have other kinds of updates. Let's say that the max, let's figure out the maximum first. Maximum is equal to the vector3, right, dot scale. And I want to take the bounds dot max, right, and the transform dot local scale. Okay, there's the local scale. And then I want to add in the transform dot position, right? And that'll give me the max, right? And I want to do that because the transform position is going to change, right? Every time I move things around, things are going to move around. They're going to be repositioned, right? So I got to keep that in mind, right? That every time I move, right, then I'm going to get my maximum extents are going to change, right? So then let's do the same thing with min. If I say min is equal to vector3 dot scale, right, and I want to pass in bounds dot min plus a transform dot local scale. Local scale is a scale that we've got that we show, plus the transform dot position. And this will give us more information about how things work. So if I go back and I try and look at some of these values, right, and I update, take a look now what I'm seeing. So here's my size, 111, right? And but take a look what I'm getting here. Don't worry about the errors because we're doing this in real time. I'm not even running this right now. So if I was to move the table down, look what's happening here. It gives me the min, negative 7.96. Here's negative 2.96, right? Plus the scale. So the extents on the y-axis is automatically calculated as the top. 7.96 on the y-axis. That's the min, right? And then what's the max? 2.04, right? So that's what's happening. So it's calculating the minimum and the maximum values, right? So if I move this up like so, right, you can see that it changes in size until I have those values change. I'm only moving it on the y-axis, and these values are changing in real time, okay? So that's what's happening there. Let's put this back to 0. Okay, what about if I move it on the other side? If I move it over here, then you can see the z-axis changes, right? And if I move it over here, the y-axis, the z-axis changes this way. And if I move it this way, the x-axis changes. So I can figure out the min, max. And when I know the min and max, what can I do? If I know the mins and max. And this is for every object. I put cube behavior on every object right now, right? So I can always find out the min and max, even if it's moving. In real time, it's going to update the min and max all the time. Yeah? Think about that for a second. All right, let's put the table back where it's supposed to go, 0, 0, 0. And then let's build upon this idea of min, max, and all this kind of stuff. Okay, so things to note, right? So bounds, we don't really care to see anymore. A list of contacts, yes, that's kind of cool, right? And we don't care really about size. That's something that we're getting from our object, size 111 or whatever. I do care about min and max. And if we look at the blue block or whatever, now this is something that's interesting, all right? So this is our size. Size is kind of relative, right? So if I was to look at the bounding area, I want to take this bounding area here, and I want to be able to, I want to draw this thing out. Okay, I want to draw it out. So let's put in some additional tools to help us. Let's put in, so I can check on the debug, that I can see in real time. When I say debug, we'll say that a public bool debug, kind of a checkbox, which is really what this is. And what debug is, we'll start it off as false. So we'll say debug is equal to false. And what we want to say is that if my debug is on, right, I want to draw some gizmos, right? Draw some gizmos. So I'm going to say I have a little private method called private void on draw gizmos, right? And what I want to say is if debug is checked on, right? If debug is checked on, only then do I want to show my gizmos. So I want to say gizmos.color, right? We're going to start off that with a color, I don't know, we'll use magenta or something. And then we'll say that, let's do a gizmos.draw wire cube. And we'll draw wire cube from the transform dot position of my object. That's the center, right? And then we need the size, right? And the size is going to be our vector3 dot scale, right? Between our a new vector3 object that we're going to pass in a couple of things, right? And the local scale. For now, let's pass in, because it's looking for the scale. Let's go 1, 1, 1. We'll read the scale in a second. And what if we did it this way? What would this produce for us? Let's make sure I'm in the right spot. Yes, I am. Transform.local scale. So again, if you notice what it needs for scale, scale is multiplies two vectors component-wise. That's what scale does. So I take the local scale, right, as an example, and I multiply it by 1, 1, 1, and that is going to be the new size of my object, right? So you could say that vector3, if it's 1, 1, 1, what's vector3 1? I could say that vector3 also has a 1, vector3.1, vector3 dot, there it is, vector3 1. What is vector3 1? It's 1, 1, 1, right? So that's another way of doing it. So I say take vector3 1, and I'm going to scale up vector3 1 by the local scale, whatever that is, and that is going to be my new size for my object. And I'm going to take that size and I'm going to put it associated with around the transform. So although I did this whole bounds calculation and size, we can do this. We can get the bounds, or we can try and get the bounds if it was a perfect cube. We can get the bounds from this object. Size, it's nice, but it really doesn't tell us what the size is. Size is like our scale, if you will, right? So we'll come back to this in a second. So let's see if what we get now. So if I look at again, this is in real time. We're running it. We're not even running this thing yet. So if I go to the table and I turn this thing on, then what I want is when I click off of it from the blue or red cube, then I want this thing to draw my magenta thing. And what I can do is if I run it, let's just run it here and see what happens. When I look at it, what I want to do is I want to see that wireframe, but I want to see it inside of, let's just don't maximize on play for a second. So maximizing on play, let's run that again. And I want to run it in the scene. So I want to see what it looks like in the scene compared to things. So what I want is when I click on this button for debug, right? When I click away, it's going to draw a magenta, kind of cube around this thing here. But anything that has this behavior on it, right? That's what I want. So same thing with the red block and the blue block. So I can turn on the red block and the blue block, turn those on debug, right? And then what I want to do is on draw gizmos, I want to be able to see this stuff as well. I want to see like a halo, if you will, or a wire cube around these things. Okay, we can stop this now, this execute in edit mode for a second. Stop that. And so we can get rid of some of these errors, right? Because these errors are generated. One thing when you execute in edit mode, guys, one thing to note is when I look at some of these things, look at that the size and the min and the max have already been decided for us, min, max, and all this kind of stuff. What we want is for all of this to be reset. We don't want any values in here at all. These are values that were set up by me because I ran it in edit mode. Please be careful about this. You don't want any of these things to be set up ahead of time. Okay, let's try this again, and let's see what happens if we run it again. Does it give me anything that I want? So run. And let's see what it does do. We can check it on other things if I wanted to run this thing. So here's what I'm running here, but what does it look like in the scene? If I check on, as an example, my table in the scene, then what I want, or any of these things here, I want to see a halo, right? I want to see a halo around these things of magenta, and I'm not seeing it. I'm not seeing it. So let's just turn them on again. So again, if I turn these on, right? So on and on, right? Then, so what happens when I turn it on? It says if debug mode is on, then I want to see my color magenta on. And it says I'm using this private void on draw gizmos object that can actually show in the inspector. By the way, if you want to test this out, just comment this part out. And so we'll always draw gizmos. So even now in the inspector, when we go back to here, we should be able to draw gizmos automatically based on the draw wire cube thing, okay? And moving it around should make a difference. Like moving this around, it should move with the cube. And that's what this draw wire cube thing's done. From the transform position, this is the middle, and the scale is the size. So take vector 3, 1, right, 1, 1, 1, and then I want to scale up vector 3a by vector 3b. So multiply those two vectors component-wise. And whatever the scale is, the transform local scale, that is also going to be a vector 3, and I should get an object back that is a vector, okay? So let's go back to what I had before. So if I say something like a new vector 3, that is 1, 1, 1, right? Let's rebuild that script assembly, right? And I want to really show when I click on this debug, or if I don't click on the debug, I want to see a magenta cube, a wire cube. Okay, so this is not working. Draw a wire cube, and it's drawing in magenta color or whatever, and it's on draw gizmos. On draw gizmos is something that happens in real time, right? For everything that happens. Let's see if we can draw a wire cube at 1, 1, 1. So who cares about this? Let's just draw a gizmo. So gizmos dot draw wire cube. Let's just draw it at, and the center will be 0, 0, 0. So new vector 3, 0. And then I'll also make it a size. So a new size calculation, right? So we'll just say size with whatever size is. So we'll draw, it according to the size. We'll do this first. So can I do this first? This is at 0, 0, 0, and 1. And we should see it in our scene, right? And I bet you I didn't have it on. Yeah, it was always there. It was always there. I just didn't have gizmos turned on. Damn it. Dang it. My son always likes to say, dang it, daddy, right? That means that it's in here somewhere, right? Wherever the 0, 0, 0 point is, right? We want to draw the extents of this thing. But notice that these are all on now. And they've been on for the whole time, right? And so I want to turn them on so we can see the extents. Notice that the extents, we want to visualize what the extents look like. So look at that. So once I have my min max, that's my scale, I can figure out that this is the size of what I'm looking at, the size that I'm looking at inside of our game, right? So we don't need to do this anymore. We can turn this on debug, and we only show up when it's running. Now, finally, gizmos are on again. Yay! And let's turn them off for blue and red blocks. We'll turn these off, but we'll only leave it on for the table. And notice that if I did that immediately, the table is on, but those two things are off in real time. So if I turn it on again for debug, you can see that it turns that on. So why is this really good? Because we can actually see or visualize the volume, right? This is what we want to do. We want to visualize the volume that I'm calculating. I'm actually calculating this volume. I'm not doing it haphazardly. That's what I'm doing. I'm calculating the volume. Yeah, I think it's a great idea, Neil. Neil saying, for the different bounciness, friction, mass, should we use enums with low, very low, high, and have function that just compares those? You can, but then what does low mean? right? What is high? What is very high? What do those things mean? You should attach numbers to those things in the enum, because you can attach whatever number you want as long as it's an integer. You're good to go, right? So for example, for very low, maybe you make it a 1, and for I mean, obviously you can make it so that you can do a switch case too to calculate what it means for you. All right, so this is the first part. So we want to be able to detect collision detection. So we're using this block behavior to do that, right? All right. What about making a little minor collision manager, not like the one that you've made with JOS? Let's do that. So create a C# script. We'll call this collision manager. Right, collision manager will be in there, and what we want is for this collision manager itself, right? We want to think about what if I had a collision manager, what would it do? First of all, let's make this system serializable. And what I want for the cube manager is a couple of properties to be exposed, or the collision manager. I want a public cube behavior, right, array that I'm going to call actors. Okay, so here are my actors, right? And inside of the start, I'm going to say that actors, I'm going to make that find objects of type cube behavior. So I'm going to say, hey, everyone that has a cube behavior on them, I want to gather it in an array of actors. That's what I want to do. And then in the update function, let's think about this for a second. I can do some kind of check AABB function, right? That's what I want to do. And we can keep it really simple. So public static will say void check AABBs, right? Between two cubes, a cube behavior A and a cube behavior B. Let's say I wanted to do that. This is kind of like your collision detection thing. And I can say that, remember, we have a lot of information now that we got from cube behaviors, right? I can say that a.min, I can do that, min, right? Because a, and I can do the x, is less than or equal to b.max .x, right? That's the first check we want to do, right? And we also want to compare that, right? So we want to say this is true, so this first part. And I also want to say that also on top of that, a.max .x is greater than or equal to b.min .x. So this is the first thing. This is the first check I want to make, right? And let's do this one. I want to say that a.min .y is less than or equal to b.max .y, right? This is the same thing, but the other way. And then a.max .y is greater than or equal to b.min .y, right? And this is your collision detection, right? And a.min .z, you can see where I'm going with this, is less than or equal to, I've just optimized it a little bit, to b.max .z, right? And a.max .z, right, is greater than or equal to b.min .z. Phew. So if this is true, that's what we're going to say. If this is true, did I put too many of those brackets in? Maybe I did. Then we have a collision, right? So I can take two ABBs and we know that there's a collision, right? But we don't want to add, we don't want to have these collisions too many times, right? So we only want to add them, we want to add these to the collision list, if you will, right? So first let's do this. Let's do a check AABB on this behavior as an example for my little collision manager that I have in play. And I want to be able to call my check AABB's function from anywhere, right? So right now it's public, static, and void, right? So again, how would I check these things? How would I check these things, right? Because I want to be able to do check AABBs from anywhere. right? So, and where would I have this thing, this collision manager? I could make it on an object, right? By the way, maybe I don't have to make it check AABBs, but what I want to do, just as a difference from what Joss has shown you, right? And again, I don't want to confuse anybody either, so I'm trying to keep it simple in my mind. So let's do a for loop where we kind of do a loop for how many actors I want to check. This is like your bad collision detection. I'm going to check every actor with every other actor. So I'm going to say, okay, for a list of actors, right, from 0 to the actor's length, and I want to check a list for the other actors. Let's do another one for J to the actors.length. So this is where I'm going to check all actors with themselves if they're all cubes, right? If I is not equal to J, so if they're not, I'm not checking the cube with itself, right? Then what I want to do is I want to do check ABBs with actors I and actors J. Wouldn't that be something I can do? So I kind of check collisions is what this is, right? I check collisions for each object. And this is only for AABB with AABB type collision detection, all right? Furthermore, when I know that I'm colliding, this is what this thing does. This collision detection algorithm is just the one from the book. It's nothing that's difficult, all right, to do. Then what if I set up a list of contacts? Remember I had that contact list in cube behavior. Here's my contact list, right? So a list of cube behaviors, right? Imagine if I want to keep track of all cubes that kind of collide with other cubes. Well, then, right, let's go back to this. I want to make that list empty at the beginning, but then what I want to do is calculate, which is in contact with everyone else. So I'm going to say, okay, if this is true, so I have a collision, then if I can say not a.contacts dot contains B, so if my contact list from A does not contain B, then what I want to say is that, well, a.contacts dot add B. I want to add B, which is the other cube, to my contact list. This is something I'm making contact with. And I can say that, well, then A is colliding is equal to true. Turn on is colliding or not, right? But what about if I don't have a collision, right? If this isn't true, so first of all, it's true, right? And so I'm not colliding. So A is not colliding with B. If A is colliding with B, then add B to the contact list. By the way, this goes retroactively for the other one, if B is colliding with A, right? However, if they're not colliding anymore and B was on the contact list, so they're not anymore on there, and I want to remove it from the contact list, right? So I can say something like else if a.contacts, and this is very simple collision detection, contains B, if it already does contain B, and I'm not colliding, right, then I can say that a.contacts dot remove B. I want to remove B from the contact list. And I want to say that is colliding, right? Now this is colliding with B is not true. Doesn't mean that I'm not colliding. I'm not colliding with B, okay? So this is kind of limitations of this idea, all right? This idea that I've got going on. What are your thoughts? So Neil says, is doing this makes the efficiency good enough? Yeah, kind of. Kind of. All right. All right, so let's see how this works. So how do I enable this thing to turn on? And do I even have to attach this thing to anything for it to work? Well, first of all, remember that this script will not be run, this collision manager, because it's of type mono behavior. It needs to be attached to something in order for it to work, right? So let's do that. So let's make it, we'll make a new 3D object. We'll call it a create empty. Sorry, we'll make an empty object. We'll call this the collision manager. We'll make it different than the game controller. and we'll zero it out. And then we'll take in this our collision manager behavior and put it on there, right? And we see that there are no actors right now. The actors list is empty, but if I run it, then we can see that we have 3 actors now. Take a look on the right here. I have the table, the blue block, and the red block. They're all part of the queue behavior. Because they're all part of queue behavior, I have a list of actors. Okay, let's take a look at the table. The list of contacts, right? We don't care about this anymore. The list of contacts for the table is empty, right? The list of contacts for the blue block is empty. Let's just kind of open this up like this. We only see the things we care about. The list of contacts for the red block, that's empty, right? So red block, blue block, table, they're all empty, right? The list of contacts. All right, cool. What if, in real time, I take this blue block and I move it down and I try to make it collide with the table. So automatically it says contacts is the table, right? And the table has contacts with the blue block. Take a look at that. I'm keeping track of the blue block and the table. I'm connecting with both those 2 things in real time. Okay? And what about if I said that the red block, here's the red block, and I want to collide with the blue block. So I go boop, boop, and I collide with the blue block too, right? So the red block is colliding with the blue block, but the blue block has both the table and the red block. And the table only has the blue block. And if I really want to, I can take the red block and slice it along so it collides with both. What about if I remove it? One goes away. Take a look at that. I can make it so it's colliding or not, but take a look how it collides, is colliding, goes away completely, right? And it's like I'm colliding with other actors. This is actually incorrect. This is colliding thing, right? I really just need a list of contacts. The only way it's not colliding is if there's no contacts. So that's something new. So that means that when I say is colliding is true, right? If I'm adding this in, I'm flipping this on, the switch. I flip is colliding is true on when I have an object. When I'm removing an object, if the only way is colliding is false from A is if, my contact list is empty. So I can check that out. I can say if, my if a.contacts, right, is empty, right? So how do I to check if it's empty? If my length is my contacts.count, right? I could say is 0, right? So it's less than equal to 0 somehow, or we can say less than 1. How about that? Less than 1, because we shouldn't have anything less. Then that would be when we're not colliding. So that's the only time when A should be not colliding is when my contacts count is less than 1. Okay. Again, this is checking for every object with every other object. Okay, that's what it's doing. Every object, 2 for loops. Every object with every other object that is an AABB type. That's what check AABBs do. Okay, which is something that you guys are basically doing. So but the idea here is we want to visualize, right? So we want to visualize these blocks in contact with one another when they turn on, right? I want to be able to do that. And I think Joss has done that for you guys. He's kind of turned on materials and all that kind of stuff. So we can switch the material color from one thing to the other thing, right? The other thing that we can make it so that the color, when we collide with 2 objects, right? We can tint the color to some other color. Like maybe what I can do is when I collide from one object to the other, I can change change the colors when they overlap. You did that, right, Miguel? With Joss? When they're overlapping, we can change the colors? Yes. So remember, when we do that for visualization purposes, right, again, in real time, right, I can switch any one of these blocks on. This is this debug mode. It's just so we can see the extents. That's what it does. We found the extents. Now, there's a couple things we don't need here. Let's optimize. We don't need size anymore. So size, not required. So if I go back to cube behavior, right, did we ever use size anywhere in here, right? So size is being used here, right? But if I didn't use size here, right, if I comment this out, are we using size anywhere else? And the answer is no. So we can get rid of size. Goodbye, size. Okay. And bounds. Bounds are interesting. We can find the mesh bounds, but the mesh bounds don't really tell us anything in terms of scale. So we can get rid of bounds because bounds we don't use. So bounds and the mesh filter we don't use. Bounds and mesh filter. So we don't use bounds. Well, we use it here. Okay, let me just go back to this for a second. We use bounds.min and bounds.max. Let's go back to that. So we do use bounds here, but we don't use size, right? So bounds is where we kind of calculate the scale. So this stuff we need, but that's all. We don't need scale. So this min-max stuff, min-maxing, is all things that can be, all of this really at the end of the day, except for your list of contacts, right? And your debug and all that kind of stuff can all be private. So min-max we don't care about. Is colliding we do care about. So we do care about this. We do care about, if we're in debug mode or not. We do care about this. And we definitely care about a list of contacts, right? Those three things we care about. But this stuff, min and max, we are calculating it. And we're fairly confident that if we made these private, that it would be okay, right? Problem is, we're accessing them. Private, min, and max, we're accessing them through our collision manager, right? That's how we're doing our check AABBs. Okay, that's how we're doing this. So that is why we're making them, that's why we need to make them public. Because public gives us our collision boundaries. That's what they are. What these are extents. So if I say header, and we'll say, collision boundaries, right? I'm creating the min and maximum for each of the objects for you. That's what I'm doing, right? These are just things we need to figure out what they are. This one is a list of contacts, right? So we'll call these collision contacts. So header, collision contacts, right? And this is just to say if it's colliding, and this is what should we call it? Cube state. Collision state. It's in collision or not collision. And this is just debug. We can keep that separate. All right, so let's see how that works instead and if that changes anything, right, for that kind of stuff. So then we can see that is colliding or not. We have a contact list and we have our min, max, and our collision boundaries down here. All right, that's what we have down here. We have bounds, right, which are also something that we have in here. Do we have to make bounds public? I think not. That we don't need to do. And that's not going to mess with anything because I want to save as much of this space as possible because we don't want to clutter our cube behavior. Right. So here's our collision context. There's a collision state is colliding as an example. So let's try this one more time. So now we can see if we're colliding with more than one, right? Cube. We don't care about this. We care about this. So if I move the blue block on top of the table, then we have table collision. If I move it away, we can see that it's not colliding with anything. But what if the red block and the blue block are colliding? So if I take the red block and the blue block, it's colliding, right? But if I move it away, it says the red block is not colliding. What about the blue block? Blue block is colliding, right? And if I move the way that the red block, blue block is still colliding because it's colliding with the table. Okay. So that's how you can make collision detection work, by using something like a collision manager. The collision manager will take to handle all things collision related, right? And right now, all I have is a group of actors. They're all part of cube behavior, right? But these actors, if you think about this, if you take it one step further, cube behavior, which is what I've kind of put together, that is something to connect actors together of type AABB. That's what they are, right? We're putting all similar actors that are of type A, B, B together. And that's what actors are, right, in my collision manager. We don't just want actors that are of type Q behavior, but rather we want objects that are collidable, right? That's what we want. And collidable objects must, if we make an interface that allows us to make a group of actors that are unlike each other, right? Then what we want is only actors of Q behavior type do we want to check ABBs out. So we go through, and every time there is an actor, and if the actor is of type ABB type, check ABBs, right? If the type is sphere, then check spheres. But we want one big actor list, spheres and ABBs and so on. So then how do you propose we change this actors list so that it includes both cube behaviors and sphere behavior, right? We have sphere behavior up here. Sphere behavior doesn't do much, right? Sphere behavior just moves stuff around, right? But we can do something similar that we've done here for my sphere, for my cube. We have cube behavior, and we have sphere behavior. Sphere behavior is a mono behavior, and cube behavior is a mono behavior. But what makes them both actors? What is, maybe there's a function or something like that that we want cube behavior to have that has calculates that makes the actor what it is, right? Make a list of mono behavior. Yes, we could. Yeah, a mono behavior type. That would be the easiest one because we already have them, right? So we can say that instead of making a collision manager with a list of cube behaviors, let's make a list of mono behaviors. Okay, if we say that all actors are of type mono behavior. So anything that's in the scene that is of type mono behavior, right? So spheres and these cubes are the same. Then what I want to do is I only want to check ABBs when for each actor, right? If, first of all, I'm not checking the actor against itself. And the second thing is that I know that the actor, both actors A and B, are both of type cube behavior. So I can say that if actors I, right, and we want to say that it's so how do we gauge the type? If I want to say type of, right? So type of in for programming in JavaScript, we use type of, right? So if type of actors I, right, as an example, if type of actors I, right, but we want to say type of cube behavior, right? We want to say that if actors I, type of cube behavior, that's what we want to kind of do. We want to do this. I want to compare this one, right, with cube behavior. So how would I fix this to make it so that it complies? How would I code this? I want to check the type of the actor. We know that the actor is of mono behavior, right? But how do I check if the actor I is of type cube behavior? How do I do that? Because I'm just getting mono behavior, right? So how do I know that the actor is what it is? Well, we can get component. Yes, absolutely. If I can say if actors I, and we know that it's of type mono behavior, right? So we want to say that get component, but we can't, is it get component? It's game object, right? We want to look at the game objects that are related to it. And then if I say get component, if this exists, if I say that actors, my game object get component, if I get component that is cube behavior, right? If I do this and if it's true, right? Can I do this? If this is found, right? If actors I is found and the same thing for actors J, if both of them, we can get cube behavior for both, right? So AA, if I can do cube behavior for both I and J, right, then can I not check this? Can I not say that this is true? Why is it giving me an issue? Because actors A, right, is of type mono behavior, and we need to cast it. So can I not cast it actors A as, cube behavior? Can I do that? Is that allowable? And can I do the same thing for this one? So, hey, if I found that two actors, I and J, are both of type cube behavior, then I can pass it into the check AABB's function to do this the same way. Is that something we can do? Let's see if this works or if it's going to crap out, right? So then I'll leave you to think about how you would add it for circle. Because one of the things we've asked you to do, well, let's see if it's giving us an issue, right? So can I just grab blue block, and what we're looking for is context for the blue block. Can I do this and then collide with this one? Oh my God, look, it's working for the blue blocks, and it's working across a block, or can say red, and I can do with both, right, by doing both of those two things. So now I can connect with those two things. Yay! Awesome, right? Okay, cool. So then what if, knowing what I know, right, I have those two blocks happening, and, well, I kind of go over here, and then I start saying things like, let's fire a sphere at it too, right? So I want to fire my spheres when I press my buttons. I want to click that button and then fire my sphere, right? And what happens if I kind of do this? I want to fire my sphere at these things, right? And here they are, right? Now, I'm not detecting red block and table, right, as part of my context, right? And the reason why this is happening is because I don't have a sphere AABB collision detection algorithm built into my collision manager. But that's easily rectified, right? Isn't it? Can I just put another function down here where I can do a public static? I don't have to make a static, by the way. I'm just making a static for now. But I can say check, AABB and sphere, where I take cube behavior for A, right, and sphere behavior for B, right, and then I do something in there where I check A, B, B, and sphere. I do that, right? And could I not do the same thing? I'll leave this to you guys to do. Could I not do the same thing with check spheres, where I say I want to do sphere behavior for A and sphere behavior for B? Isn't that something I can do? And then what I can do, and forget what, I'm running out of time here, else I would code it for you. But could I not just do the same thing? I can just do the same idea, copy, and paste, right? So I can say, so these are the cases. So the cases where both things are cubes, the case where one is a cube and the other is a sphere, right? And I say that instead of checking ABBs, I check ABB sphere, right? Where I pass in the second one as sphere behavior, right? And could I not do the same thing for the last one, which would be if both of them were spheres, right? And then I say, well, I want to pass the first thing as sphere behavior, and the second thing as sphere behavior, we'll just check spheres. Can I not do that? So I'm presenting this to you as an alternative. All I'm saying is it's not better than what Joss has done for collision detection, but it might be easier, right? And all this massive for loop, it's checking all the types, every type, right? So the types that we care about, cube, spheres, and sphere cube, and cube spheres, all that stuff. And once we have that, then we can really take this and extract it into its own, kind of method. And we'll call this kind of like, check collisions. So, or we'll say collision detection. Or detect collisions. How about that? Detect. Terrible, Tom. collisions. Detect collisions. So the detect collisions method is going to be called every frame, and the detect collisions method is going to call up check ABBs, check ABB sphere, and check spheres. And one thing that we have to note is that we need some stuff similar for spheres as we do for cubes. We don't have these things in place. That's why I'm saying we have to code it differently. I need some way, the things that the cube needs and the sphere needs, I already have mins and maxes for the cubes, and I need some other things for the sphere. Sphere behavior has a bunch of things. Right now, we only have speed and direction, but obviously for collision detection, we need a center, right, which is the transform dot position, and the radius. I need to know what the radius is of that sphere, right? So let's see what else we say here. So you'll think that the object will not keep bouncing forever, yeah? Or like make the object will not affect by the velocity if they are not moving. I think, it can happen, right? But it's again, what you're trying to do is you are trying to have a simple way of managing collisions with all objects on the scene. And you want to make it at one central spot, similar to what Joss has done, I'm sure. But I'm just doing it in a way that I can mark objects as, for now, the object will move forever. But yeah, what you can do is you can make it so that when it goes far away, you're talking about like spheres, right? Or you can make it so that it when it goes past a certain point beyond the origin, right? So example, we know that in the game world, we start at 0, 0, 0, right? So if the transform dot position is beyond a certain point, then get rid of it. So example would be, let's take a look at this. It's going to ignore everything right now, okay? But let's see what it does. So what I mean is, if I took my sphere behavior, just for now, and I say that when the transform dot position, if the transform dot position is beyond the magnitude is more than, let's say, I don't know, 100 units, we don't care about it anymore, right? So that's what we want. So we want to say something like, if my transform dot position dot magnitude, right? And if that is greater than, let's say, 100 units, right, then I want to destroy the object in the sphere. So I want to destroy this dot game object. There we go. So destroy it, right? And destroy one thing instantiates it, which is something I'm doing in game controller, where I'm just instantiating an object. It's not very efficient and whatever, but here I'm destroying the object, right? So I can do that. And if it's, let's say, if it's greater than 100 units away from origin, if sphere is more than 100 units away from the origin, right? Right, that's what I'm saying. So if it's far, far away, then delete it, right? So, and if you notice that if I did that, then it would be pretty cool. So I've started you on a journey, and I'm not sure if you want to take it, but having a collision manager and doing it this way might be something where, let's see if I can shoot that ball out there. And then if it's more than 100, then notice it just keeps on, it'll eventually will disappear when it's out of sight. Look. And then no more, right? So from a unit perspective, I can do it like close by, right? But if I was to cast the object from, from here, and if it bounces or whatever, it won't go forever. It won't go forever. Remember that I have a very slow frame delay. My frame delay is 200. I can make something like a lot faster. So let's say 100 to make it, something that is more reasonable, right? So something like that. And it doesn't matter if I make these things go all over the place now, because they're just going to delete themselves after they go farther than about 100 units. We can't see 100, right? Okay. Questions around this stuff? Yeah, timer's okay too, but making it go further out. Again, magnitude using square root, so we can be careful about that. We might want to use squared magnitude, right? So there's no square root, because that's what magnitude does at the back end. from a efficiency perspective. We don't want to do magnitude for anything. We always want to use square magnitude. That's what we want to do here. Okay. All right, any questions before we go for the date? Okay, just a reminder. So next week, there will be no lecture or labs as normally. I don't think Joss probably said the same thing. He probably said there's no labs next week. We're just gonna be there for exam help. So that's what we're there for next week. So please make sure you attend those things and do that. Okay. And the same thing goes with me for next Thursday. I will not have I'm not going to have a lecture. Obviously, it's going to be the final test, and I'll be here for test help. So that's it for me. And I know there's a couple questions. So for the people who have questions, stick back. I'll stop recording now, and I'll go from there. Okay. Thanks, Neil. Take care. I'll stop recording this now. All right.